So, imagine you're filling out this massive complicated form on your phone, right? You've been typing for like 5 minutes straight.
Oh yeah, we've all been there. It's the worst.
Exactly. And you just tilt the screen sideways to get a better look at a text box. And in that exact fraction of a second, the operating system literally burns down the app's entire interface, just rebuilds it from scratch.
Completely from the ground up, yeah.
Right. And everything you just typed could be entirely wiped out in an instant. And you have to ask, why? So welcome to this deep dive into the DNA of Android applications.
Yeah, it's a fascinating topic.
It really is. Today, we're taking a huge stack of highly technical sources ranging from official developer documentation to insider senior level interview cheat sheets. And we're extracting exactly how apps survive the absolute chaos of your daily taps, swipes, and rotations.
And I think the craziest part of that chaos is realizing that, unlike traditional computer programs, Android apps don't even have a starting line.
Wait, really? No starting line at all?
No, not at all. I mean, if you look at standard desktop software, right, you double-click an icon, the program finds its main function, and it basically just runs straight from top to bottom.
It's like a script.
Exactly. But Android completely throws that centralized concept out the window. It's this highly volatile, dynamic ecosystem where control is constantly being passed back and forth.
So if there's no front door and no main function, how does anything actually boot up? I was really trying to wrap my head around this architecture, and the most fitting analogy I could pull from our sources is, well, it's like a high-security hotel.
A high-security hotel, I like that.
Yeah. So every single app you download from the store gets its own completely isolated room, which is its own virtual machine.
Right. And what's fascinating here is the underlying mechanism enforcing that strict isolation. The Android operating system is actually built on a multi-user Linux kernel.
Okay, so it's Linux under the hood.
Yep. And it actively enforces something called the principle of least privilege. So the second you install an app, the system silently assigns it a unique, invisible Linux user ID.
Invisible meaning the app doesn't know about it.
Exactly. The app itself doesn't even know this ID exists. It's just a fundamental security barrier baked into the OS.
See, that makes perfect sense when you ground it in daily use. I mean, this is exactly why that sketchy flashlight app you downloaded can't just quietly read your banking app's passwords in the background.
Right, because as far as the operating system is concerned, the flashlight and the bank are two entirely different Linux users locked in completely different hotel rooms.
They're literal strangers.
Total strangers. And because they can't access each other's memory, and because there's no master main function running the entire show, the Android system itself has to step in as, well, the ultimate hotel manager.
Right, it has to orchestrate everything.
Exactly. It constantly monitors the device, deciding when to spawn an app's process, and more importantly, when to assassinate it to free up RAM.
Assassinate it. That's a great word for it.
It really is ruthless. And for the system to exercise that kind of granular control, apps have to be constructed from distinct modular building blocks, 4 core components to be exact.
And those are activities, fragments, services, and broadcast receivers, right?
You got it. Those 4 are the foundation of everything.
Okay, well, let's unpack the parts of the app we actually interact with first, like the UI frontline. That's your activities and your fragments. Based on the documentation, an activity is basically just a single screen, right?
Yeah, that's the best way to think about it.
So, your email inbox list is one activity, and then you'd have an email, and that full screen reading view that pops up, that's a completely different activity.
Precisely. They're independent modular containers. And because the OS is, like we said, a ruthless hotel manager constantly hunting for free memory, these containers are chained to a very strict life cycle.
A life cycle, like they're born and they die.
Exactly. They transition through heavily monitored states. So you have onCreate to initially wire up the user interface, and then onStart when it actually becomes visible to the user.
And then onResume when you can actually touch it.
Right. onResume is when it's fully interactive and ready for touch input. But then the teardown begins. You get on pause if it loses focus, but is still partially visible.
Like if a transparent pop-up appears over it.
Exactly. Then on stop if it gets completely hidden by another app, and finally on destroy when it's just wiped from memory entirely.
Okay, let's unpack this. Because that screen rotation trick we discussed earlier, the one from the interview cheat sheets, is absolutely wild.
Oh, it really catches junior developers off guard.
I bet. Because when you physically tilt your phone to landscape mode, Android doesn't just dynamically stretch the pixels out. It aggressively calls onDestroy, trashes the entire activity, and then loops all the way back to onCreate just to rebuild the screen.
That's right. It burns the whole stage down.
Why on earth would the system be designed to be so fundamentally destructive? It just seems wildly inefficient.
Well, if we connect this to the bigger picture, it's actually a brilliant solution to hardware fragmentation.
Cool.
Think about it. Android runs on thousands of different screen sizes, resolutions, folding displays, all sorts of form factors. When you rotate a screen, your physical constraints change completely.
Oh, I see. A horizontal layout is a totally different shape.
Exactly. It might require a totally different navigation bar or completely different high-resolution graphics to look right. By forcing the activity to die and be reborn, the OS guarantees the app reloads the absolute most optimal graphical resources for that exact new configuration.
Okay, I get the visual part. But wait, if the entire stage burns down, wouldn't the user lose all the text they just typed into that form we talked about?
Yes, and that specific challenge is exactly what separates junior developers from senior ones.
Really? Just handling a screen rotation?
Oh, absolutely. Because you can't just leave your critical data sitting in the user interface. Developers have to explicitly hook into that lifecycle using tools like onSave instance state to safely cache the data before the fire and then inject it back in after the rebuild.
Wow. So it forces developers to architect resilient applications from day one. You can't be lazy about state.
You really can't, and that leads perfectly into the push toward fragments. Activities are these massive, heavy containers getting constantly destroyed.
Right, the docs describe fragments as like reusable chunks of UI that live inside an activity.
Exactly. You can swap them in and out dynamically without burning down the whole screen, like having different panels on a tablet interface.
But the cheat sheet highlights a massive trap here. It says fragments actually have two distinct life cycles.
Yes. And it's one of the most common ways complex apps crash.
Wait, if the fragment is just the logic managing the view, the actual pixels on the screen, shouldn't they just die together? Keeping a fragment alive in memory while the view is gone sounds like a massive recipe for a memory leak.
It is a huge trap. You see, a fragment has its own life cycle representing its baseline existence in memory, but the view has a completely separate life cycle representing what's actively being drawn by the GPU.
Oh, so they are detached.
Right. The OS might destroy the view to save graphics memory when a fragment is placed in the background. That calls onDestroy view. But it keeps the fragment object itself alive in memory so it can be quickly restored later.
Okay, so if a developer writes code telling the fragment to hold on to a reference of a view that the system just actively destroyed,
Then the garbage collector can never clean it up.
oh no.
Yeah, that destroyed view is permanently trapped in memory. As the user navigates the app, it bloats, gets slower, and eventually crashes with a catastrophic out-of-memory error.
That sounds like a nightmare to debug.
It really is, which is why modern Android development heavily emphasizes a property called View Lifecycle Owner. It strictly forces developers to only interact with the UI when the view's specific lifecycle is active, completely ignoring the fragment's broader memory state.
That makes total sense. Protect the memory at all costs.
Yeah.
But what happens when you minimize that email activity entirely? Like the screen is gone, the UI is paused, but the app still needs to, say, download a gigabyte-sized video attachment.
Right, you can't just stop that because the user looked away.
Exactly. That requires an entirely different system that doesn't rely on pixels. We basically need a backstage crew.
And that's where we get services and broadcast receivers. Because, not everything requires a visual interface. Services handle those long-running, invisible tasks.
So keeping with our analogy, think of a service like a mailroom down in the basement of the hotel.
Perfect analogy. It doesn't care what the lobby looks like or if the lights are off. It just processes data independently. Meanwhile, broadcast receivers are these tiny system-wide listeners waiting for global announcements.
Like battery at 5% or Wi-Fi connected.
Exactly. Just listening for the system to shout something out.
Well, actually, I spotted a massive contradiction in the official documentation here that I have to ask you about.
Oh, what's up?
The docs clearly state services are designed for heavy background work. But then right below that, in bold red letters, it explicitly warns that a service runs on the app's main thread by default.
Ah, yes. The classic main thread trap.
But the main thread is the UI thread. If a service is supposed to be downloading a massive file, why is it freezing the entire screen unless the developer explicitly writes manual code to build a new background thread? That seems completely backwards for a modern OS.
It really does sound crazy today, but if we connect this to the bigger picture, this raises a critical point about the philosophical evolution of Android.
Okay, how so?
Well, Early versions of the operating system gave developers an enormous amount of unrestricted freedom. The OS provided the raw tools and basically assumed developers would use them responsibly.
That sounds dangerous.
It was. You want a service, it belongs to your app, so it defaults to your main process. The assumption was that any competent developer would naturally spin up secondary background threads for heavy network or database lifting.
And I'm guessing that immense trust was wildly misplaced by the developer community.
Oh, completely. It led to a dark era of terrible battery drain, overheating phones, and frozen interfaces.
Yikes.
Apps would quietly spin up background services, execute heavy database queries directly on the main thread, and the user's entire device would lock up. The Android engineering team had to aggressively pivot. They shifted from a philosophy of trusting developers to heavily restricting them.
The era of the ruthless hotel manager really took over.
It had to. Today, if you want a service to run continuously in the background while the user isn't actively looking at your app, you generally have to use a foreground service.
The foreground service, what's the difference?
The major catch is that a foreground service forces the app to display a highly visible, unswipeable notification. You can't hide in the shadows doing secret work anymore. The user has to explicitly know you are consuming that battery.
Oh, like the Spotify playback notification. You physically can't swipe it away while the music plays.
Exactly. That's a foreground service keeping the music alive. And those system restrictions keep tightening with every OS update.
I read about some of the changes in Android 14.
Yeah, the docs mention that in Android 14, the system actively defers broadcasts. If your app is cached in the background, the OS won't even wake it up to tell it the Wi-Fi status changed until the user physically opens the app again.
Wow, so they are really locking it down.
Totally. Broadcast receivers went from being these powerful, silent background triggers to tiny, highly restricted 10-second gateways. You get the system message and you get out. If you need more processing time, you have to formally hand the job off to the OS.
So we have these heavily isolated UI sandboxes and these tightly restricted background workers. But for a smartphone to be useful, apps have to actually talk to each other, right?
Of course.
So how does a camera app pass a fresh photo to a messaging app if they are locked inside completely different, secure Linux user IDs?
They utilize the asynchronous communication system built directly into the OS kernel, which are called intents. They are essentially the standard messengers bridging those isolated sandboxes.
And looking at intents, the core distinction between explicit and implicit intents completely flips how we think about software communication.
It's a really unique paradigm.
Right, because explicit intents are like a direct, certified letter to a specific person.
Yeah.
You write the exact Java class name on the envelope, like start the compose email activity inside my own app.
Yeah.
You know exactly who is getting it.
Very targeted.
But implicit intents, they're like standing in a crowded town square and just shouting, who here knows how to send an email?
Yeah.
You don't care which app answers, you just declare the action.
Yep, and then the system looks around and says, well, Gmail can do that, and Outlook can do that, and gives the user a prompt to choose.
But what's crucial to understand here is how does the operating system actually know who in that town square can fulfill the request?
Right, the OS isn't guessing. It relies on the ultimate rulebook of every application, which is a file called the androidmanifest.xml.
The ultimate VIP guest list.
And the public billboard, really. Absolutely no component, no activity, no service, no receiver can exist or be launched if it isn't explicitly declared in the manifest.
So it's the absolute source of truth for the app's structure.
Exactly. And for those implicit intents, an app uses the manifest to declare what are called intent filters. Gmail's manifest literally states, I have an intent filter for the action of sending an email.
Okay, that makes sense.
But, this system isn't without risk. If an app broadcasts an implicit intent containing sensitive user data without properly securing it, a malicious app could simply declare a matching intent filter, intercept the message in the town square, and steal the payload.
Which is exactly why the manifest is also the central hub for security permissions, right?
Yeah.
It's where the app has to formally beg the user for access to the camera, the microphone, or the contacts.
Right, you have to ask for the keys.
Speaking of contact, how does a messaging app actually read your friend's phone number if those numbers belong to a completely different app's secure database? Like, you can't just pass an entire database through an intent.
No, you definitely can't. That requires the fourth and final core component, a content provider.
Okay, a content provider.
The Android system will never allow the messaging app to just directly open the contacts database file. Instead, the contacts app creates a content provider to act as a heavily guarded teller window.
A teller window. I like that.
Yeah, it uses specific URIs, which basically look mathematically identical to web addresses, to say if you have the correct permissions declared in your manifest, you can query this specific URI to get contact names.
So it securely shares structured data without ever exposing the raw database architecture itself.
Exactly. It's highly controlled access.
Okay, so we've got the 4 foundational building blocks: activities, fragments, services, and broadcast receivers. And they're all glued together by intents in the manifest.
That's the classic Android toolkit.
But here's where it gets really interesting, because the sources make it undeniably clear. If you walk into a senior developer interview today and just list those 4 things, you're getting laughed out of the room.
Oh, 100%. Knowing the raw materials of concrete and steel is fundamentally different from knowing how to engineer a skyscraper.
Right.
The modern Android landscape demands a master plan. It requires highly decoupled, layered architecture.
Yeah, the documentation breaks this down into distinct layers. You have the UI layer, the data layer, and this vital domain layer sitting right in the middle. But the biggest revelation for me was that the traditional components we just spent all this time dissecting are practically shrinking.
Shrinking is a great way to put it.
Like, an activity today is almost entirely hollow. It's just a dumb, empty container. And services are barely ever used directly by developers anymore.
It represents a massive paradigm shift. Think back to the quicksand of the activity lifecycle we talked about earlier.
The screen rotation fire.
Right. If you stuff your complex network calls, your database saves, and your intricate business logic into a UI component that gets ruthlessly murdered every time the user rotates their phone, your app is going to crash constantly.
It's a guarantee.
So modern architecture physically separates the data from that brittle user interface.
And this is where view models and work managers step in to do the heavy lifting, right? But how exactly does a view model magically survive the fire of a screen rotation when the activity doesn't?
Well, the underlying mechanism is that the view model isn't deeply attached to the activity's immediate volatile life cycle. It's held in memory by a completely separate system component called the view model store.
Oh, so it lives outside the blast zone.
Precisely.
Yeah.
When the screen rotates, the OS trashes the activity instance, but the view model store keeps the view model object perfectly intact.
That's clever.
So milliseconds later, when the new activity is rebuilt for the landscape orientation, it just reconnects to the exact same view model in memory. The data never skipped a beat.
So the activity is literally just a blind screen looking through a window at the smart view model.
That is exactly what it is.
And what about Work Manager? How does that replace the old system of manual services?
Well, instead of a developer manually building a service, spinning up complex background threads, and fighting all those OS battery restrictions we talked about, Work Manager defers the task entirely.
Defers it to who?
To the OS itself. The app tells the OS, hey, whenever the phone is finally plugged into a charger and on unmetered Wi-Fi, upload this massive video file.
Oh, wow. So you just give it conditions.
Exactly. And then the app can completely go to sleep. The OS's internal job scheduler wakes up the device at the optimal time, executes the work efficiently, and goes back to sleep. It's infinitely more battery efficient and infinitely less prone to crashing.
Which brings us back to the specific architectural layers you mentioned. The data layer handles retrieving that information from the network or a local database. The UI layer just displays whatever it's told to display. But what exactly is that middle domain layer doing? Why is it necessary?
The domain layer. This raises an important question about business logic. Let's say you're building a massive e-commerce shopping app. The UI layer handles drawing the checkout button. The data layer handles executing the SQL query to save the final order. But calculating the final price? Applying a 15% holiday discount, adding regional tax codes, verifying inventory limits, that complex math belongs entirely in the domain layer.
So it's the actual brain of the app.
Yes. It encapsulates specific use cases so they can be easily tested and reused anywhere in the app without cluttering the UI or the database code.
That plays directly into the ultimate philosophies of modern development the sources talk about: the single source of truth, or SSOT, and unidirectional data flow, UDF.
Those two concepts are the absolute holy grail of app stability. Single source of truth means any piece of data like the items currently sitting in your shopping cart only exists in one definitive place.
Usually a local SQLite database in the data layer, right?
Exactly. The UI layer doesn't store its own local copy of the cart. It purely observes the database through the view model.
So if a user clicks the Remove Item button, the UI doesn't just casually delete the graphic from the screen.
Never. That would break the synchronization. The UI simply sends an intent or event downward.
Okay.
The unidirectional data flow dictates that user actions flow down to the domain and data layers. The database officially updates the single source of truth, and then the fresh, mathematically correct cart automatically flows back up to the view model and pushes into the UI.
So the UI is just a blind mirror reflecting the database state.
Exactly. It purely reacts.
It essentially takes the unpredictable, chaotic OS lifecycle completely out of the equation. You let the hotel manager burn down the reams all they want. The valuable luggage is safely locked in a vault down the street.
That is the perfect way to visualize it. The OS handles the rigorous hardware constraints, and the layered architecture protects the user's data integrity.
We've covered some serious ground today. I mean, we started in a software world with no main function, exploring secure multi-user sandboxes and invisible Linux user IDs.
We really went through the entire history.
We did.
Yeah.
We watched activities and fragments burn to the ground just to survive a simple screen rotation, dug into the hidden background mechanics of intense and deferred work managers, and finally mapped out the highly disciplined, layered architecture that keeps modern Android running smoothly.
You know, if we project this developmental trajectory forward, it leaves us with a profound question about the future of the operating system itself.
What do you mean?
Well, if modern architecture is aggressively pushing to make activities and fragments hollow shells that merely observe state, and complex background execution is being entirely outsourced to system-level APIs like Work Manager.
Will the operating system eventually abstract away these complex life cycles altogether?
Exactly. Could we realistically see a future where developers don't even need to know what onResume or onDestroy are, leaving them to focus purely on state, design, and data flow? Or will the harsh physical battery and memory constraints of a mobile device always force us to manage the chaos manually?
Man, that is a huge question. It's definitely something to keep in mind the next time you boot up Android Studio. Or even just download a new app on your phone. Keep questioning the code, keep challenging the documentation, and keep exploring. Thanks for joining us on this deep dive.